Welcome back, Night Owls. This is Dr. Nighttime, and tonight I'm going to show how conservation of energy can be used to make a number of rather complicated, scary-looking physics problems easier to solve. I'll note that this video will go through some progressively harder and more complicated physics problems. It's entirely possible that if you're part of the way through a physics course, you'll be able to understand and be familiar with some of the earlier problems, but not the later ones. If you're currently taking a physics course, I recommend watching this and just seeing which problems I talk about. You don't have to understand the whole thing, but that then later on, when you start seeing some of the problems that might seem familiar, like, hey, didn't Dr. Nighttime talk about that in that video? You can look back at it again a couple times throughout your course and see how a couple of techniques here, or one particular technique here, will enable you to find the solutions a little more easily than you might otherwise think. So first thing I'd like to go through is that you actually were probably using a conservation of energy technique very early on in your physics course. They just didn't call it that. They called it kinematics, particularly the time-independent kinematic equation. Typically, early on in a physics course, after they've talked about the basics of vectors and forces, they'll introduce the equations of motion. And one of the ones they'll introduce is the one that doesn't depend on time. Final velocity squared minus initial velocity squared equals 2 times acceleration times distance. Now, let's look at the special case where the acceleration involved is gravity, which is a classical case that you'll look at that early on in the physics course. You'll get Vf squared minus Vi squared equals negative 2 GD, where if I take G to be positive just because it's the magnitude of the acceleration, but of course, as you climb higher up, you're traveling more slowly, not more quickly. Now what happens if, just for the fun of it, I multiply through by the mass of the object m? mvf squared minus mvi squared equals negative 2 mgd. Then if I divide by 2, I get 1/2 mvf squared minus 1/2 mvi squared equals negative mgd, where d is the change in your height. Well, if you remember, kinetic energy is 1/2 mass velocity squared. Potential energy is mass times gravitational acceleration times height. So I get my change in kinetic energy, my change in 1/2 mv squared, equals the negative of my change in potential energy. When kinetic energy goes up by some amount, potential energy has to go down by that same amount, and the other way around. And so we could apply that to a standard simple kinematics problem. You drop a ball from a rooftop 60 meters above the ground. Air resistance is negligible. What is the ball's speed at impact? So I could do it the kinematics way. Vf squared minus Vi squared equals 2gd. You said drop a ball, not throw a ball, so Vi is 0. Vf squared minus 0 equals 2 times negative 9.8 meters per second squared times negative 60 meters. Vf squared equals 1176 meters squared per second squared. Take the square root. Vf equals 34.3 meters per second. Compare that to conservation of energy. Now you might think we can't actually calculate the energies because we don't know the mass of the ball. And that's right, we can't calculate the individual energies. But we can still solve for what we need to. 0.5 mvf squared minus 0.5 mvi squared equals mg h final minus mg h initial. V initial is 0, h final is 0. Notice I changed the signs here, right? And I get 0.5 meters times Vf squared equals mass times 9.8 meters per second squared times 60 meters. I get Vf squared equals 2 times 9.8 meters per second times 60 meters. I crunch through, I take the square root, and I get the same 34.3 meters per second. Now let's look at a more complicated problem. And part of what makes this problem so complicated is because I included something that involves torque. If you haven't learned about torque and angular acceleration and angular momentum yet, don't worry about that. So you might not be able to follow fully the logic here, but when it comes to it, and you start learning about it, this will make a lot more sense. You have a 20 kilogram block suspended around a 10 kilogram ideal pulley. By ideal pulley, when we give the mass of the pulley, that means you don't assume it's a massless pulley, but assume that it's uniformly distributed about its center. The mass is uniformly distributed about its center. Assume there's no friction with the pulley around its axis. And assume that the rope traveling along the pulley moves without slipping. And that's connected to another block, also 20 kilograms, on a frictionless surface. They're initially held steady and then released. What will the acceleration of this system be? When you say acceleration of the block, that means this one's going to be moving down with some speed and some acceleration. This one's going to be moving to the right with some speed and some acceleration. What will that acceleration be? So the straightforward way of doing this without conservation of energy, you can set it up okay, but then trying to solve the system becomes less than pleasant. Not terrible, but could be better. So we set up everything we need for a free body diagram. 20 kilograms here, 20 kilograms there, 10 kilograms here. And we do our force body analysis. So we look at the bottom box. It's 20 kilograms times G, that's going to be the force pulling it down, minus T1. T1 is going to be the tension in the rope at this point. T2 is the tension in the rope up here. Note that because we don't assume the pulley is massless, we give the pulley some mass, that means it'll actually take some net torque to make the pulley start rotating. So the two tensions can't be equal. So we have T1 down here, T2 up here. 20 kilograms times G pulling down minus T1 pulling up equals the 20 kilogram box times its acceleration. Okay, that's an equation. We can't solve for anything in particular because we've got two unknowns of A and T1, but okay. Pulley has the hardest equation. We know that the moment of inertia of a uniform disk is 1/2 mass times the square of its radius. So I of the pulley, I is moment of inertia, is going to be 5 kilograms times r squared. We know that alpha, the angular acceleration, is a, this linear acceleration, over r. We know that because the rope isn't slipping. As this block goes down by some amount, it pulls this rope some amount, it makes the outer edge of, a point on the outer edge of this pulley rotate by some amount, and so the angle in radians is going to be the total distance divided by the radius. Notice I didn't give the radius of the pulley. It's okay. It comes out in the equation, right? And in the algebra, we'll find that the radius of the pulley is actually irrelevant. We know that the torque, the net torque on the pulley, equals moment of inertia times acceleration. So now we can calculate the net torque. If you remember torque, it's force times perpendicular distance. Since the rope is always tangent to the pulley, the perpendicular distance will just be the distance from the edge to the center. So you get T1 times r going one way, T2 times r going the other way. The T1 times r goes in the direction of acceleration, right? Intuitively, right? You don't have to be an engineer to realize that when you let go of this block down here, it's going to go down, not up. Right? So you get T1 times r minus T2 times r equals 5 kilograms times alpha. Or sorry, 5 kilograms times r squared times alpha, A over r. The r squared over r cancels. You get T1r minus T2r equals 5 kilograms AR. Divide through by r. I said that the r would just disappear from the algebra. There it goes. Goodbye. We get T1 minus T2 equals 5 kilograms times A. So we've got a second equation. We still can't solve for anything in particular because we've got two equations in our three unknowns of T1, T2, and A. Then you look at the top box. This has the easiest equation. The only force it feels is T2. So T2 is the net force. That's going to be 20 kilograms, the mass, times the acceleration of A. So we finally get 3 equations in our 3 unknowns. I'm not going to actually solve them here. It's a linear 3x3 system. If you want to go pause the video here and solve it as a matrix, go ahead, but I won't ask you to do that. Last week, in a video, I said pause the video while I snuck off to have a cotton candy break. I won't do that to you this time. This week, don't bother pausing. It's going to be a mess to solve. I'm going to show you an easy way to do it that doesn't involve solving the 3x3 system. It's the kinetic energy approach, or conservation of energy approach. Also called the Lagrangian approach, if you wanted to name it after a scientist. So we look at the potential energy of this whole system. The only thing here that has potential energy is the box itself, or sorry, this overhanging box, 20 kilograms times the height. Then there are 3 objects that have kinetic energies. This one has a translational kinetic energy, mass times velocity squared over 2. Same with this one, mass times velocity squared over 2. And this one has moment of acceleration times angular velocity squared over 2. So we add those up, we get 1/2 20 kilograms v squared plus 1/2 I, where we said that I is 5 kilograms times r squared, times omega squared, I'll deal with omega in a moment, plus another 1/2 20 kilograms times v squared. We said that this I is 10 kilograms times r squared. Omega, angular velocity, if you remember your relationship between translational and rotational kinematics, omega equals v, velocity, over r. So we square our omega, we get v squared over r squared. We multiply this by an I that has an r squared in it, the r squareds cancel. So we get kinetic energy equals 1/2 20 kilograms v squared plus 1/2 times 5 kilograms times v squared plus 1/2 times 20 kilograms times v squared. Total 22.5 kilograms times v squared. So we have our potential energy, which is this constant, where g is a constant, it's a constant, times your displacement, x. You have your kinetic energy, which is a constant, times square of velocity. And we want to say that the change in one of them is equal to the negative change in the other. To do that, we're going to need to know how a square quantity changes. And if you're in a high school class, particularly an AP but not calculus-based AP physics class, this is the formula that they're a little scared to try to teach you. But I'll try explaining it here. So to find the rate of change of the area of a growing square, right, that way we can find the rate of change of a square quantity. So suppose a 6-inch square is growing at the rate of 2 inches per second. At what rate is the area itself growing? So one way you could do is you could approximate it with the area now versus 1/100th of a second from now, and divide that by the 1/100th of a second. So you compare the smaller square, 6 by 6, to the larger square, 6.02 by 6.02, and see what that gets you. It gets you 24.04. That's approximately 24, which is 2 by 6 by 2. More generally, if I imagine that this square is growing, how much extra area is added? Well, this gray area up here is going to be 6 times the 0.02, or sorry, times the, it's the 6 times the 2 inches per second times however much time has elapsed. And then this one is 6 this way, and 2 inches per second times however much time has elapsed. So you'll get 6 times the rate at which that length is changing, plus this length times the rate at which that length is changing. And then what about this little tiny white area? Well, I could say that this is going to be this tiny little area, this tiny little length, which for small amounts of time is negligible, times the rate at which it's changing. So for really, really small amounts of time, that actually goes away. So, some notation that's used by mathematicians, engineers, physicists, and other scientists. A dot over a quantity means the rate at which something is changing. So we get that the rate at which x squared is changing is 2 times x times the rate at which x is changing. We get this length times this little piece here, an x times an x dot. We have another x here times this x dot. And then this little bit will be x dot times something too small to worry about. And that's the formula we'll need. X squared dot, rate of change of x squared equals 2 times x dot. So using this dot notation, where dot means rate at which something is changing, we can express our conservation of energy equation in terms of dots. We can say KE, kinetic energy dot, equals negative potential energy dot, right? In order to say that if kinetic energy goes up by some amount, potential energy must go down by that same amount, that means the rate at which one of them is changing has to be the negative of the rate at which the other one's changing. We said kinetic energy for this problem was 22.5 kilograms times velocity squared. We said potential energy was negative 20 kilograms times g times x. So let's dot both of these. This one, we said this is going to be 2 times, obviously multiplying out by 22.5, right? If I multiply by some constant, then it's just changing by that constant, right? Or it's changing by that times as much. So I get 45 kilograms, right? Because I multiply by this 2. I said that something squared dot is 2 times the thing times the dot of a thing. So rate of change of a square quantity is 2 times the value itself times the rate at which that value is changing. So 45 kilograms times velocity dot equals, now I look over here, there are no squares, it's just 20 kilograms times gravity times x dot. But let's think about this. When I say rate of change of velocity, that has a name. V dot is just a. And when I say rate of change of position, that has a name. X dot is just v. So I can rewrite this as 45 kilograms times v times a equals 20 kilograms times g times v. Divide both sides by v. I get 45a equals 20 times g. Gravity. I get acceleration is 4/9 g. And I get it without needing to solve a system of 3 equations in 3 unknowns. Now I can verify that this a satisfies the equations, right? It's easier to verify a solution to a system of 3 by 3, a solution of 3 equations and 3 unknowns, than it is to solve it from scratch. So if I have this reason to believe that a is 4/9 of g, let's check. Our first equation we had from the top box was 20 kilograms times g minus t1 equals 20 kilograms times a. If I say a is 4/9 g, algebra happens. I get T1 equals 100/9 kilograms times G. Because if this A is 4/9 G, I just subtract the 4/9 G from either side. I get 20 kilograms times 5/9 G minus T1 equals 0, and solve it from there. Then I looked at the equation I got from the pulley. When it all simplified, if you remember, that was T1 minus T2 equals 5 kilograms times A. Well, if I know T1 is 100/9 kilograms times G, then I could say 100/9 kilograms times G minus T2 equals 5 kilograms times 4/9 G, right? A is 4/9 G. Crunch my numbers, I get T2 is 80/9 kilograms times G. And so, assuming my guess for A was correct, then I should be able to plug these in, and it should be right. This T2, which I'm claiming is 80/9 kilograms times G, and this A, which I'm claiming is 4/9 times G, that should satisfy their relation, and it does. 80/9 kilograms times G does equal 80/9 kilograms times G. So it works. So we get that this solution does satisfy our system of 3 equations and 3 unknowns, and we were able to get that without needing to solve a matrix, right? Or without needing to do some crazy substitutions. All we had to do was express everything in terms of potential and kinetic energy, know our rule for rate of change of the square of a quantity, and apply, all right, so x dot, rate of change of x, is velocity, v, and v dot, rate of change of velocity, is acceleration, a. Plug those in, realize we can divide both sides by v, and just get the equation easily in just a few lines. Now let's try a harder problem. Suppose friction is involved. You might think you can't do conservation of energy with friction. Energy isn't exactly conserved, but you know exactly how conserved it isn't. What do I mean by that? Well, I can figure out the work done due to this friction force. Work done equals energy added, or if it's negative work done, it's energy removed. And just throw that into my system. So suppose we have the same setup as before. Now the top ledge has a coefficient of kinetic friction mu k equals 0.2, which means we can get a frictional force. Now we want to solve for the acceleration. So again, our Newtonian system, we have that same, we'll do the 3 free body diagram analyses, force on bodies, right? We'll just have a friction force there. It's going to get us a slightly scarier looking matrix. I'm not even going to do it that way. We'll just do the energy equations. Instead of saying kinetic energy final plus potential energy final equals kinetic energy initial plus potential energy initial, I say it's all that minus the work done. I know that the work is going to be negative because friction always removes energy from the system. So rearranging, I say kinetic energy final minus kinetic energy initial equals negative potential energy final minus potential energy initial minus work. And so I can say, let me take the rate of change of everything, and it should still work. Right? If I look at the absolute change in something, I can say, well, what's the rate of that change? If the change is equal or equal and opposite at every point in time, then the rates should also be the same. So Ke dot equals negative Pe dot minus W dot. We already know how to get Ke dot. We already know how to get Pe dot. What about W dot? Well, if you remember, your work equation, work equals force times distance. So it's going to be force of friction times your distance traveled, x. W dot is going to be force of friction, that's a constant, times x dot, which is v. Right? Rate of change is just going to be force times velocity. Crunch the numbers in. We figure out that with a coefficient of friction of 0.2, gravity is 20 kilograms. It's a horizontal surface, so normal force is equal and opposite to gravity. So 0.2 times 20 kilograms times g times the same velocity that didn't go anywhere. W dot equals 0.2 times 20 kilograms times g times v. So, shoving this all into a single equation, we have the same Ke dot that we had before, 45 kilograms VA. Potential energy is going to be 20 kilograms times GV. And the work done is going to be 0.2 times 20 kilograms times GV. Divide through by V again, 45A equals 20G minus 4G, which equals 16G. So we get A equals 16G over 45. Notice that before, we had A equals 20G over 45. Now it's down to 16G over 45. This agrees with our intuition that adding friction slows the whole thing down. So even when you can't say energy is conserved, you can still do the bookkeeping and accounting for it by saying, all right, we know energy is lost. How much energy is lost? At what rate is energy being lost? And just factor that into your equations. And again, it allows you to solve the system without solving the 3x3 matrix. And if an instructor really wanted to make sure you knew how to do it, that instructor could have more pulleys and more systems and give you like a 6x6 system, and you'd have to do a 6-way substitution. Okay, or just do these. Yeah, it'd be a few more terms, but you would be able to combine your like terms. Your kinetic energy terms would just add and be constant times v squared. And your potential energy terms would add and be constant times x. One last problem I'd like to go through, and this gets into some particularly advanced stuff that even a lot of Physics 1 courses omit and save for something later. Oscillatory motion, where you have a spring involved. So intuitively, I'm getting rid of friction here, and there's a reason why. Setting up the system, we were able to treat friction before as just, well, we know that friction is going to go one way and it's going to remove energy. We knew which way friction was going to point, because we knew as soon as we let go, the system's just going to rotate this way. Right? This block's going to go down, this one's going to go forward, friction's going to point that way. Intuitively, when I have a spring, I let go, it moves, and then the spring stretches and pulls back. And so as it's going back and forth, the direction of that friction is going to go back and forth, The equation itself is going to involve absolute values and signin functions, which is not appropriate to introduce at the introductory physics level. So I'm omitting it. If you're watching this video, chances are the course you're taking also omits that. They might include friction against a liquid. That's its whole separate case, where the friction ends up being proportional to the velocity. You could do that by hand relatively painlessly. I won't, not tonight. So that's why I kind of have to remove the friction here. Anyway, non-friction case, but now there's a spring of stiffness K equals 200 newtons per meter attached to the top block. The spring starts at its resting length. And again, we want to know, I guess I didn't put the question here, but we want to know the behavior of the system. We know it's going to oscillate and accelerate, so the stuff we want to know is stuff like how far will it oscillate? Because it's frictionless, it'll presumably return to its original position. How long will it take to do that? That sort of stuff. We want to describe the behavior. All right? So now we have an additional potential energy term. Kinetic energy is still the same as what we had before, 22.5 kilograms times v squared. The potential energy, there's a potential energy of this block, 20 kilograms times g times x, or I guess negative 20 kilograms times g times x, because as x moves forwards, the block moves downwards. Now you have an additional 1/2 kx squared here from the spring. So it's negative 20 kilograms times g times x plus 100 newtons per meter, 1/2 k, times x squared. Ke dot is the same as it was before, 45 kilograms VA. Pe dot, rate at which potential energy is changing, is negative 20 kilograms times g times v, remember x dot is v, plus 200 newtons per meter x times v. Remember, rate of change of x squared is 2x x dot. X dot is v. So we set these equal to each other. Remember, Ke dot equals negative Pe dot, so 45 kilograms VA equals 20 kilograms GV minus 200 newtons per meter XV, divide by V, divide by 45, or 45 kilograms, we get A equals 20 over 45 times 9.8 meters per second squared minus 200 over 45 times x per second squared. The per second squared is just for dimensional analysis. Acceleration has to be in meters per second squared. X is measured in meters. Now notice I can factor out 200 over 45. I get that this is equal to negative 200 over 45 times, or 200 over 45 per second squared times x minus 0.98 meters. So I get that the acceleration is proportional to the distance from some equilibrium point or some center point, if you will, in the opposite direction. Which you've seen in springs. There's one other situation where you saw acceleration being proportional to distance from a certain point and in the opposite direction. We've seen it in uniform circular motion, specifically when you're looking just for the x-coordinate or y-coordinate of the force or acceleration in uniform circular motion. So what I'll do, imagine for the moment that simultaneous to this system oscillating back and forth, so this top block goes back and forth, back and forth. Obviously it's not going to actually collide with a pulley. I drew the picture badly. But as it's going back and forth, imagine that simultaneously there was a particle rotating around in this blue circle at constant speed. It turns out that the x-coordinate of the particle rotating around the blue circle would be directly above or below the point on this block. Because we say that for uniform circular motion, right, we say total acceleration is v squared over r. The x component of acceleration is v squared over r times x minus the center over r. So v squared, negative v squared over r squared times x minus the center. Well, if that's the equation that describes uniform circular motion, but it also describes the acceleration of this block, then we know that these two need to be behaving in the same way. If the same equation applies to both of them, the motion needs to be the same. So what we're given is the acceleration, obviously in the x direction, because this block is moving side to side, is negative 200 over 45 per second squared times x minus 0.98 meters. So this center point of this circle must be 0.98 meters away. So the radius of the circle must be 0.98 meters. Our v squared over r squared must be 200 over 45. Well, we know our r is 0.98 meters, that's distance to the center of the circle. So we get our v over r is 2.108. Our omega, our angular speed, if we imagine that this is rotating around and around, that we've got an imaginary particle rotating around and around. I know it's a little abstract to imagine a particle here, but this provides a way of explaining the sinusoidal motion without needing to solve differential equations. If we have this imaginary particle going in a circle, rotating in a circle, at constant speed, we know that that will have that equation, horizontal component of acceleration equals this constant times x minus center point in the negative direction. We can then, using what we know about circular motion, solve for the angular velocity. That is how many radians per second. It's going to be 2.108 radians per second when we crunch our numbers out. V over r is just going to be the square root of this number. And so then if we want to figure out the amount of time it takes to return to the initial position, we'll say that's going to be 2 pi times 1 over omega, right? To get seconds per radian, 1 over omega will get you seconds per radian. You're traveling 2 pi radians, so seconds per entire rotation is going to be 2 pi times 1 over omega. Alternately, if you didn't want to think in terms of angular velocity, if you tried to solve for v, you could get that, and then you'd acknowledge that to go all the way around, you have to travel 2 pi r. And do distance equals rate times time. So time equals distance divided by rate, and try to do it that way. So now what we found is that this system will be oscillating. It'll go back and forth with a radius of 0.98 meters, or diameter of 1.96 meters, and it will take whatever 2 pi times 1 over 2.108 is. That's the number of seconds it'll take to return to its initial position. One last thing I'll want to introduce. We can actually set this up as an equivalent mass spring system. This sort of sinusoidal motion is often called simple harmonic oscillation. Well, let's look at the simplest of simple harmonic oscillators. Suppose we have a horizontal oscillator. I should have drawn a table support here so that there's no gravity. It's just going back and forth. I have a spring of some unknown k and a mass of some unknown m. For that, my potential energy is 1/2 kx squared. My kinetic energy is 1/2 mv squared. PE dot is going to be kxv. KE dot is going to be mva. Our equations have PE dot equals 200 newtons per meter times x minus 0.98 meters v. Alright, so I do the substitution, right? Y equals, or x tilde equals x minus 0.98. I just do that linear shift. I'll find that it's not oscillating about the point 0, it's oscillating about the point x equals 0.98 meters, but I get an analogous potential energy. And kinetic energy, that's much simpler. It's just 45 kilograms VA. Alright, so that means if I plug directly in, if I say P dot equals KXV, well, and I do the shift so that this becomes an X or an X tilde, then that means it's as if my spring constant is 200 newtons per meter, which in this case it actually is that much. And for my kinetic energy, it's as if my mass is 45 kilograms. The combined mass of everything involved is more than 45 kilograms, but it's not a simple harmonic, it's not the simplest of these harmonic oscillators. If I want to reduce it to an equivalent mass spring system, I find that if I did have a K of 200 newtons per meter and a mass of 45 kilograms, I would have the same potential energy equation and the same kinetic energy equation, up to a shift of 0.98 meters. Right? There's that linear shift. So I change where my equilibrium point is. Now, you might have seen the formula that angular frequency for this simplest of harmonic oscillators is square root k over m. Sure enough, if I pretend that my k is what it actually is, it's 200 newtons per meters, but I pretend that my m is 45 kilograms, I take square root of 200 over 45, I get the same 2.108 radians per second. So I can say my actual oscillator has this complicated setup of a spring and some masses. I could even have multiple springs if I wanted to make it weirder. But I could say, if I had a simpler version, the kinetic energy would be the same if I just had one mass and one spring and nothing rotating around. I'd get the same kinetic energy equation if I just had this m, and I get the same potential energy equation if I just had this k. I can use the equivalent system to get a really simple formula for omega. If you're still watching, thanks for watching this far. Okay, I've kind of introduced topics that typically come up at best throughout multiple points, very different points within one course. Often this is spread out across multiple physics courses. Sometimes they even delay some of this to a vibrations course in engineering. So I definitely recommend re-watching this if you're working on an engineering problem and say, oh yeah, wasn't there some way of doing that with energy and simplifying it down? Feel free to watch this again if that comes up then. And I hope you found this useful. As always, if you like the way I explain things and want to arrange private lessons, click the link in the description. And until next time, this is Dr. Nighttime wishing you a good night.